Advanced laser retroreflectors for solar system exploration, geophysical networks, and lasercomm. Just push the red. Yeah.
Thank you very much. Good morning, everybody. What I will talk about is the research we are carrying on at INFN in Frascati, in particular at the SEF lab, which is a space characterization facility devoted mainly for laser retroreflector arrays. And I will talk about some of the application we have been working on solar system exploration mission, in particular the moon and some for Mars, but also other possible applications. First of all, I would like to acknowledge my colleagues, and collaborators, both from Italy, especially the SEF lab team, and from US, for example, the Professor Doug Curry from University of Maryland, which is in the audience. So first of all, let me talk about our affiliation with NASA Survey. It's been almost a year. We signed, our president of INFN signed this affiliation. The goal is to jointly exchange expertise and study new technologies for laser ranging retroreflector arrays, to characterize them, design them for solar system exploration missions. So first of all, I would like to talk about our activity. It's been almost 9 years. We are working on developing and optimizing a laser retroreflector array for the next generation laser ranging activity. Right now on the moon there are the 3 arrays brought by Apollo missions and 2 by Lunokhod missions. They've done a lot of science, planetary science, and physics, and a lot of stuff. We are thinking about a new generation of retroreflector, which is basically a solo big retroreflector of 10 centimeter diameter. Why moving from an array of retroreflector to one single retroreflector? Because of the librations, there is a source of error, a source of uncertainty, which nowadays is one of the main source of uncertainties for the laser ranging measurement. And so basically with a single retroreflector you cancel out with this uncertainty given by the fact that a pulse is retroreflected and many pulses interfere and give a bigger pulse, so giving an uncertainty. With a single retroreflector you refer to a single point. This is a nice picture that compare an Apollo retroreflector with our big retroreflector. Right now we have 3 of them. We are in the process of taking another one, so we will have 4 of them. This is a nice picture that explains, that shows the retroreflection. As you can see, the reflection of the 3 edges of the retroreflector that converge in the camera of my phone. And the specification on this retroreflector are really tight in order to have the best performance. What is the science? As I said, some planetary physics, lunar interior that has been done till now also by laser ranging, but also we hope on the improving tests of general relativity and some other science. Here we have a list of papers we have published. So to enhance some of the science that can be done with lunar laser ranging. This retroreflector is a retroreflector of 10 centimeter front face. Is uncoated. It means that is a bare prism of fused silica, which is the material. And we have done a lot of simulation in order to find the optimal configurations for these retroreflectors. And we found 2 of them. I will talk about one, which means it is a perfect retroreflector. Well, basically to cope with the velocity aberration, the effect of the relative movement between the ground station and the retroreflector, you usually in retroreflector for satellites around the Earth or even on the Moon, you augment the angle between the faces from 90 of a factor of fraction of an arc seconds in order to move the intensity from the center. So we changed the orientation of the retroreflector with respect to laser beam. We changed the orientation of laser polarization, linear and circular, and we changed the value of these dihedral angle offsets to find the best configurations. Here's, for example, here is the far field diffraction pattern of a retroreflector, and we looked at the intensity of this tiny segment because the velocity aberration for the Moon is a shift on the right in this far field diffraction pattern domain. And the optimal configuration we looked at was that the one that had the variation of the intensity with respect to the average, which was the smallest, because laser ranging station cannot, I mean, very few can control the polarization. Actually, I think that there is just one in Matera in Italy, because they have an experiment that controls the polarization. So this is a plot which variation of intensity in terms of optical cross-section, which is 1 million square meters. After that, we are doing some thermal simulations, basically changing the temperature distribution inside the retroreflector, both in just changing the temperature difference between the front face and the tip and on the front face, and applying that using a thermal software simulation. We simulate during a lunar day the environment, so the temperature distribution inside the retroreflector, and we look how the intensity changes with that. Parallel with that, we are doing an intense activity of laboratory testing. For those who have been in Frascati in May, you have seen our test facilities, and we are doing that for optimizing the housing structure, the holding structure of the retroreflector in order to keep the temperature difference low inside the glass. We were talking about on Tuesday about exchanges between research centers, national agencies, and private companies in order to bring payloads on missions. We just signed on May an agreement with Moon Express in order to bring 4 of our payloads, 4 of our retroreflectors on their missions on the Moon. We are very excited about that. Moving to another type of research, this is an instrument called INRI, Instrument for Landing Roving Laser Retroreflector Investigation, which is a small retroreflector array, lightweight, compact, maintenance-free, is a passive device that could help enhance some of the science that can be done for Mars mission in particular. Well, an accurate precision of landing of landers, or accurate position of rovers that go around Mars, as ranged from a satellite around Mars. could give some test and diagnostic for lasercomm capabilities, give some georeference exploration activity, define a meridian zero of Mars, which right now is given by the Airy Zero crater, but with laser ranging this could be much more precise. Multiple of these arrays could define a geophysical network, could aid some LiDAR space landing. A rover could put one of these devices in an interesting place, and for future mission, this could be aid by could aid a landing, as has been done for the docking using laser ranging, and also some relativity tests, some physics science. This is a cartoon that explains what I've been saying. So the rover going around the surface of Mars and be interrogated by laser, even in near infrared, so using laser altimetry, and also in visible, could be just carried one of these devices, but also multiple devices, and a rover could put them somewhere in some interesting places around the surface of Mars. This is a slide taken from a LAD presentation that explains, that LAD has proven some interesting results of lasercomm, and retroreflectors could aid some test and diagnostic for early phases for lasercomm missions. IRI is a spherical cap of 8 retroreflectors arranged as in this picture. Each retroreflector is half an inch diameter, and they are made of fused silica, and retroreflectors are silver coated. This is the far-field diffraction pattern of the whole device as taken from above, and basically is a big peak, and we are looking at the intensity in this on this ring. So we take the average on this ring, because differently from the moon, a spacecraft could move in many directions above this device. And here is to show just how the intensity varies as we move, as we change the inclination of the laser along this along this line, along this x-axis. As you can see, there is a peak when the laser hits the CCR just above, because the active reflective area is the whole area, the whole front face of the CCR. If we rotate the device having this line aligned with the x-axis, what we'll have is just that intensity would be, at this level until we reach 38 degrees, which is the intensity of this, the tilt of this retroreflector with respect to the vertical. This device and also other type of device, it depends on the missions, could be used on many other missions. For example, Europa and Enceladus are right now they are thinking about just going around with spacecraft, so orbiters, but in the future for landers the idea would be the same. Even for Phobos and Deimos, of course, depending on the missions, we could use this tiny device or other different dimensions. But also for asteroids, near Earth asteroids, we could put a laser retroreflector array on the surface of an asteroid. So to summarize. we have a unique experimental and design expertise in laser ranging instrumentations for Earth systems, but also for solar system exploration. We have been designing a laser reflector array for moon laser ranging, and we're happy to have signed an agreement with Moon Express in order to carry one of our payloads on their mission. And we have been designing also this tiny Earth reflector array for many types of missions, Mars, even on the moon and planetary moons. So, thank you for your attention.
Somebody have one quick question? Thanks.
Thanks.
The next speaker is Kurt Klaus, a comparative assessment of delivering consumable